Half hours left in class, kidding. Alrighty, so now we're on to section 6.8, which deals with mechanisms and arrow pushing. And we drew curved arrows in chapter 2 that showed resonance. However, that just showed the delocalization of electrons around a molecule or ion, whereas the curved arrows that we're going to use here are used to show how electrons move as bonds are being broken and bonds are being formed. Remember, this is not what we did in chapter 2. We were just showing electron delocalization. Now we're actually showing bonds being broken and formed. Remember that we use them in acid-base reactions. For example, where we see the base, we take a pair of electrons, and since the base is a Lewis at base, it's an electron donor. This arrow here represents bond being formed. So bond being formed. And the second curved arrow here, that means that you're breaking this bond between the hydrogen and the conjugate base of the acid. So bond broken. So we're forming a bond and we're breaking a bond. And there are four main ways that electrons are going to move in polar or ionic reactions. Nucleophilic attack, which we use Na as an abbreviation for. The next one is the loss of a leaving group, LLG. Proton transfers, PT. And a rearrangement. And thus, every time we draw a curved arrow mechanism, every curved arrow is going to be one of these four types of movements of electrons. So let's start with the nucleophilic attack. A nucleophilic attack represents a nucleophile attacking an electrophile. Here we have bromide. Well, bromide has a negative charge right on it, so we know it's a nucleus lover. It's a nucleophile. And if we have a carbocation, well, that's definitely an electrophile. It's seeking electrons. And so we draw one curved arrow that shows this bond here being broken. We show the flow of electrons starts on the pair of electrons, the negative charge, and the head ends up on the positive charge. In the electrons, these two electrons from the bromide, they end up being shared rather than transferred, right? These two electrons are shared in this bond right here, a nucleophilic attack. Now, sometimes we can have a nucleophilic attack where we have simultaneous bonds being formed and bonds being broken. Take a look. Here's an example of a nucleophilic attack that requires more than one curved arrow. We have an alcohol. Now, remember, I told you that that is a weak nucleophile, but it's still a nucleophile. And then we have our electrophile. How do you know this is an electrophile, Mr. Dion? Well, we have a carbon atom here. It's attached to an oxygen and a chlorine. We know that oxygen is the second most electronegative element in the periodic table, so it's pulling electron density away. And then chlorine is more electronegative than carbon, so both of these atoms are pulling electron density away from the carbon, which renders the carbon partially positive. So we have the nucleophile. The lone pair is partially negative. We start with the tail on the pair of electrons on the oxygen, and we draw the head of the arrow ending up on the carbon that is our electrophile. But carbon cannot have 5 bonds. You could not draw this. So don't draw it. It's going to be a heresy. But you could not draw the arrow. Where's my electrophile? Here we go. Just like this. If you were to do this and just say, here you go, done. That's good. You can't do that because then you'd end up with this where you have your carbon with your double bond to oxygen, your chlorine, your methyl group, and then an oxygen that has a positive charge on it like this. That's impossible. We can't do that. Why? Because this carbon has 5 bonds. This, no, we'll just put here, no such thing. Okay, that doesn't exist. And so we have to show the bond being formed, this bond, but we have to break a bond between the carbon and the oxygen. Why do you pick this bond, Mr. Dion? Well, what's weaker, a sigma bond or a pi bond? A pi bond is weaker than a sigma. Therefore, that is the bond that we draw breaking, and we end up with this intermediate. So nucleophilic attack can be comprised of more than one arrow. And I also told you that a alkene or a pi bond can act as a nucleophile. This thing here, this is called sulfur trioxide. So this is SO3. sulfur trioxide, just a little bit of covalent compound nomenclature for you there. But sulfur trioxide is very electrophilic. Well, why would that be? Same rationale that we saw before. The sulfur is attached to 3 oxygens that are just yanking electron density away like crazy. Therefore, this sulfur is really partially positive. And we know that a pi bond is weaker than a sigma bond. So therefore, the electrons in the pi bond can behave as a nucleophile, and they can attack the sulfur. We have to break a pi bond here. Why? Because the sulfur can't take on another bond, and we end up with this carbocation on our ring here and the negative charge on the oxygen. Note that only one of the carbon atoms from the pi bond uses the pair of the electrons, and the other one ends up with a positive charge. Any questions about nucleophilic attack? Any questions about that? Okay. So that's the nucleophile attacking. We saw we could have a strong nucleophile, a weak nucleophile. Well, let's move on and let's talk about a loss of leaving group. Let me remind you again, the new nucleophilic attack, we use Na. The next one is the loss of leaving group. We use LLG. So loss of leaving group involves the heterolytic bond cleavage and loss of some kind of group that takes a pair of electrons. Let's look at an example here. We have tert-butyl bromide, and then you just have the bromine leaving as a bromide. And when it does, it takes the pair of electrons in this bond. Remember, a double-headed arrow represents the flow of 2 electrons. Where does the tail start? The tail is starting on this bond. That means both of those electrons in this bond are ending up on the bromine to make a bromide. And that means that now your carbon is only going to have 3 bonds. So this carbon is sp2 hybridized with an empty p orbital. Therefore, it's a carbocation. Now, we can also have situations where a loss of leaving group will take more than one curved arrow to show the loss of that leaving group. This is a really cool example here. This is used in something called a nucleophilic aromatic substitution reaction, which is neither here nor there today. That's something that's covered in organic chemistry too. But the bottom line is that we're losing the chloride, right? We're breaking the bond that I'm highlighting in here in yellow. If you look at all the other curved arrows in here, none of the other arrows represent a bond being broken. And this bond here shows the start of this negative charge causing the loss of the leaving group, so to speak. So let me just draw what you get from this. You'd have your 6-membered ring. You didn't touch this bond whatsoever. You still have this, which you didn't touch. But look, you broke this bond and you formed a new bond here. So let's draw that bond in there. You broke this pi bond and put a new bond here. So now you've got an aromatic ring. Now you've only got one bond between the aromatic ring and the nitrogen. You didn't touch any of this, so you still have this bond over here. This oxygen is negatively charged, and now you've made a new bond here. So now you've got 2 bonds over here, like this, and your nitrogen has a positive charge. And what happened? You lost the chloride ion, loss of leaving group. The next one is a proton transfer. A proton transfer requires 2 curved arrows. Sometimes you'll see chemists draw it like this as 1 curved arrow. I'm just going to ask you, do not do this. Do not draw this. You'll see chemists who know what they're doing, you know, who are seasoned veterans of curved arrow drawing. They will do that, but don't do that in Chemistry 3101. We're trying to learn the subject, so let's do it the proper way. And here we have the oxygen behaving as a Lewis base, donating a pair of electrons. And we have the acid, hydronium, donating this proton. And then we end up with this oxonium ion. So when you have an oxygen with 3 bonds, 1 lone pair, and a positive charge, we call this an oxonium. And then you end up with water being regenerated too, right? We end up with water being formed over here. And then again, the deprotonation, just always try to draw it as two curved arrows like this. I'd say this is correct. And this, there's nothing wrong with it technically, but just don't do it. So there we go, the proton transfer. Multiple arrows may be necessary to show the complete electron flow when a proton is exchanged. For example, take this proton transfer right here. We have 3 curved arrows. The hydroxide, which is a base, is accepting a proton, but then to show what's happening to the pair of electrons in this bond, they're saying, okay, well, I'm going to take those pair of electrons, make a pi bond here, and then I'm going to break this pi bond and put the lone pair up here. And what you end up with is something that's going to look like this, okay, which is actually part of a resonance hybrid. Okay, you could draw either one of these as resonance structures. And so the proton transfer, you could either draw it like this or like this. They both represent the same thing because either way you get the product that is part of the resonance hybrid. So that's proton transfer. And the last one is a rearrangement. I forgot proton transfer. For that we use PT. And the rearrangement, the abbreviation we use for that is RGT. And rearrangements are based on a carbocation's ability to become, or just to become more stable. Okay, so let's go over this. It says carbocations can be stabilized by neighboring groups through slight orbital overlapping called hyperconjugation. This is a word that comes up over and over in organic chemistry, so I'm just going to highlight that, hyperconjugation. So what they're showing here in this picture is this. I'll draw the Lewis structure. It's basically, it's not basically, it is. It's an ethyl carbocation, okay? And what they're showing you is that the positive charge is on a carbon that's sp2 hybridized and it has an empty p orbital. So empty p orbital, and that's why we have a positive charge. But what happens is there's some slight orbital overlap between the sp3 hybridized orbital of the methyl group and the hydrogen, where it can kind of overlap with the empty p orbital, and it kind of puts some electron density in here, and that stabilizes it. And so what's the conclusion we can draw is that the more alkyl groups we have surrounding our carbocation, the more stable it is, because those neighboring alkyl groups are going to donate or stabilize it through hyperconjugation. So a summary is what's shown right here. This is something you need to memorize. Memorize that the most stable carbocation of all is going to be one that's surrounded by 3 R groups. We call that a tertiary carbocation, very stable. Then you go to a secondary, which only has 2 R groups, a primary, which is not very stable at all. It's only surrounded by 1 R group. Then you go to a methyl, which is really, really unstable because we have no neighboring alkyl groups to stabilize the carbocation. And carbocation stability is something that comes up over and over and over in organic chemistry. And so what's this whole idea of rearrangements? Well, here's the answer. If a carbocation can undergo a rearrangement to become more stable, it will do it. Check this out. There's 2 types of carbocation rearrangements that we're concerned with in Chemistry 3101. The first one is what's called a hydride shift. Now remember, a hydride is a hydrogen with a lone pair. So this is a hydride, whereas if you have H+, that's a proton. Okay, so those are 2 different things. Proton has no electrons, but a hydride has a pair of electrons. So a hydride shift is if you look at a carbocation and you look at a neighboring carbon and see if it has a hydrogen. Okay, you ask yourself, well, if I was to move that hydrogen and this pair of electrons over to where that carbocation is, now this carbon only has 3 bonds and it's a carbocation, but you end up with something more stable because we go from a secondary carbocation to a tertiary, right? This carbocation is surrounded by 1, 2 carbons, whereas this tertiary carbocation is surrounded by 1, 2, 3 carbons. So we're making something more stable. The other thing is a methyl shift, 1,2 methyl shift, same rationale. Here we have a secondary carbocation, but if we took this neighboring methyl and put it and its pair of electrons into that empty p orbital, then we end up with a tertiary carbocation. So shifts can only occur from an adjacent carbon. That's why they're 1, 2. And shifts only occur if you get a more stable carbocation. So we have to go from primary to secondary, or secondary to tertiary. And then a tertiary can even rearrange under certain circumstances. So when we put everything together, nucleophilic attack, proton transfer, loss of leaving group, and rearrangement, we can get reaction mechanisms. And multi-step reaction mechanisms are just a combination of those four patterns. Take a look at this neat reaction here. We're starting with this alcohol, and we're making this alkyl halide. But look at all the different things that are happening. Let's go through it step by step. The first thing that's happening is the transfer of a proton. The hydroxyl is gaining a proton. Then we end up losing a leaving group. The leaving group just goes away. We lose water as our leaving group. We have a secondary carbocation here, which undergoes, this is a methyl shift. It's a carbocation rearrangement, but this one happens to be a methyl shift. This methyl moves over to make a tertiary carbocation, and then the bromide comes in as our nucleophile, does a nucleophilic attack, and there you have it. And not all reactions that we're going to look at will involve every single type of pattern. You know, some of them might only involve one or two, okay? But sometimes we'll see all of them, like we do in this reaction. And oftentimes you're going to see two patterns occur at the same time. Check this out. We see the hydroxide here acting as a nucleophile. It's attacking the electrophilic carbon. So this is a nucleophilic attack. But then the chloride is leaving at the same time. And so this arrow down here represents a loss of leaving group. They're happening in a concerted fashion, which is nothing more than a fancy word that means at the same time, concerted. There we go, nucleophilic attack and loss of leaving group, and that brings us to a question. It says, for the following multi-step reaction, look at the curved arrows and identify the sequence of arrow pushing patterns. Remember, the four patterns are, in no particular order, nucleophilic attack, proton transfer, loss of leaving group, and carbocation rearrangement. Every one of these steps, step 1, 2, and 3, they all have to involve one of those types of mechanisms. So let's look at the first step. Step 1, we're starting with this ester, and then we're going over here to this carbanion. So step 1 is all of this together, okay? Up to this point, this arrow here is part of the next step. Could anybody tell me what's going on right here with these two curved arrows? What does that look like to you? A proton transfer, nucleophilic attack, loss of leaving group, or a rearrangement? Anybody have an idea? What does that look like to you? Is there a particular atom that's being transferred as we go from here to here? What's the atom that's involved? It's a hydrogen. And the hydrogen is moving over to the hydroxide, right? You're forming a bond, right? You're forming water in this step right here. And so if we're taking a hydrogen, I would say that that would be a proton transfer. First step is a proton transfer. Yes, absolutely. What about the next step? We have something with a negative charge on it, and then we're making a bond between that and this electrophilic carbon over here. How would you describe this step that I have shown here? Would that be, and I'm talking about this one here, how would you describe that? Would that be a proton transfer, loss of leaving group, nucleophilic attack, or a rearrangement that's occurring here? Absolutely, it's a nucleophilic attack, isn't it? Right, this is my nucleophile. This is my nucleophile. This is my electrophile. And this is a nucleophilic attack. And then what about the last step? We see that we're losing something. So how would you categorize this one here if you're losing something? Absolutely, it's a loss of leaving group. Right, so loss of leaving group. There we go. So the first step was a proton transfer. The second step was a nucleophilic attack. And the last step was a loss of leaving group. And in case you're wondering, this alkoxide, this is the leaving Leaving. Son of a gun, what's going on? This is the leaving group. All right, here we go. So a little bit of practice in recognizing those. Some more kind of rules that you need to know about drawing curved arrows. Just a few kind of things that you have to look out for, things you don't want to do. You know, one thing that you don't want to do is you don't want to draw your arrows incorrectly. Okay, so a curved arrow is always going to start on a pair of electrons. So the curved arrow should always start on a lone pair or on a bond. Okay, so we'll put here lone pair or bond. That's where your arrow is always going to start. You see that both of these arrows, they start either on a pair of electrons or on a bond. This one is wrong because this arrow does not start on a lone pair or a bond. Okay, it's definitely not starting on a lone pair. This is a bond and this is a bond, and the arrow is not starting on the bond. So that arrow is incorrect. We'll put big no-no there. Let's see, never place the tail of a curved arrow on a positive charge. That would be a big no-no. So let's say you had, you know, something like this, a carbocation. You would never start the tail of an arrow like that. That would be a huge, huge no-no. The arrow always ends on a nucleus where the electrons become a lone pair, or they end up between two nuclei, which means they're forming a bond. So one or the other. Let's see here. For this first one, we're starting on a pair of electrons. We're going over to this nucleus. We're forming a bond. This one ends up on a nucleus. We're forming a lone pair. Avoid breaking the octet rule. So if you ever end up making 5 bonds to something, that would always be wrong. So you see how this arrow here, it just looks like you're forming a new bond. You'd have to make a bond and break a bond in order for it to be correct. You cannot have 5 bonds to a carbon. Next, any curved arrow drawn should describe one of the 4 patterns. So it's either going to be a nucleophilic attack, loss of leaving group, proton transfer, or a rearrangement. If it doesn't follow one of those patterns, it's wrong. There's something really weird about it. This arrow here is just totally jacked up. It violates the octet rule. It doesn't match any of the 4 patterns. Therefore, it is just out in left field and totally, completely incorrect. But let's try drawing a curved arrow. Now, this is not easy for me to ask you over Microsoft Teams, but I'm going to ask you. If I put in the lone pairs on the water molecule, like this, could anybody tell me how like unmute their mic and describe, or they could even type it in the chat, describe to me how you drew the curved arrow to make the new bond, because there's one new bond formed. This is bond formed. And if you could tell me which one of the patterns is shown here, like we need a curved arrow somewhere here. Could anybody tell me where they start and where it ends up? Could anybody describe what the curved arrow would look like here?
Would it start on one of the lone pairs on the oxygen, and then it would end pointing at the carbon that is positive in the first one?
Absolutely. I couldn't have said it better. I could not have said that better myself. Okay, so what Tracy is saying is, she said, well, this is obviously my electrophile. It's got a positive charge right on it. Okay, it's hungry for electrons. And this is my nucleophile. It's not a strong nucleophile. It's not negatively charged, but it's a nucleophile. And so what she says is, well, you start your curved arrow on a pair of electrons. You can pick either one, but it's going to go over here. And where's it going to head to? It's going to end up on our positively charged nucleus. Yes, I see somebody else typed in the chat. You're both 100% correct. Beautiful. Excellent. Give me a thumbs up if you follow me on that curved arrow. Of course, it's something that has to be practiced. Okay, cool. Cool. What you're doing is not easy, okay? Remember, if it was easy, anybody off the street could do it, and I guarantee you could go walk up to somebody at Target and show them this. Hey, could you draw me a curved arrow? What? Security? All right. Well, one more thing we'll have to go over before we take a look at the practice problems, and that's carbocation rearrangement. So look, something you're going to have to train your eye to do is anytime you see a carbocation, all chemists, whether it's you, me, doesn't matter who it is, you always have to look at it and ask yourself, could there be a carbocation rearrangement? Yes or no? And this is something that you're going to get better and better at doing. Okay. So here we have a secondary carbocation, right? This carbon is attached to 2 carbons. That means it's secondary. Now, the question is this thing going to undergo some kind of rearrangement? Yes or no? Well, what were the rules? We can either shift a hydride or a methyl, and it has to come from an adjacent carbon. So where are the adjacent carbons? We've got an adjacent carbon here, and we've got an adjacent carbon here. On the one in red, the only thing we have are 2 protons, right? These 2 protons. Since they're both identical, I'm just going to write one of them in. So I'm just going to write, there's a hydrogen. Whereas on the carbon in green, there's the methyl group on it, and there's also the hydrogen. And I'm not kidding. You have to weigh in your mind, would this shift and maybe give me something more stable? Would this shift and maybe give me something more stable? Or would this shift? Maybe one of them will. We haven't answered that question yet, but you have to be able to weigh out all of those in your mind. Let me show you one really quickly. Okay, and I'm going to probably have this on another slide because I just probably do, but let's imagine we shifted the proton in red. Okay, what would that look like? The tail of your arrow is going to start on a pair of electrons, the pair and the bond, and then it's going to end up on the nucleus, like that. That would be a rearrangement. Now let's draw what you would get from that. Let me erase this. So you would end up with these 2 methyl groups. Now this carbon has 4 groups attached to it, so it's sp3 hybridized, and you've got the methyl and you didn't touch any of this. So now this carbon is the one that's electron deficient. It lost a pair of electrons, and so it's a carbocation. This is a secondary carbocation. Do you think this would occur? Yes or no? Not a trick question. Never try to fool you. Do you think this would happen? Does this look reasonable to you? Thanks, Clinton. The answer, thank you, Tracy. The answer is no, because you're not making anything more stable. So what about the methyl or the blue hydrogen? Would either of those shift? Let's take a look. Okay. What if you moved the hydrogen over? This is the blue hydrogen from the previous slide, this one here. If you were to move that one over, okay, as a hydride shift, then you go from a secondary carbocation to a tertiary carbocation. Is that going to occur? The answer is you bet your bobby socks. It will occur. Why? Because you end up with something that's more stable. So let's write down here. This will happen. Okay, look deep into my eyes. I'll hypnotize you. Anytime a carbocation rearrangement can occur and make something more stable, it's going to happen. Now, if you're wondering, well, why wouldn't the methyl shift, Mr. Dion? Why wouldn't the methyl group here, why doesn't that shift? Because same rationale. Let's look. I'm going to erase this arrow. If the methyl group shifted over like this, let's draw what you'd end up with. You'd end up with this, where you'd have a methyl group over here. Then you have this. You have a secondary carbocation again. Not going to happen. It doesn't help you in any way, shape, or form. So you have to be able to be cagey enough and be experienced enough to look at this and say automatically, yes, this hydrogen is going to move, because when it does, I go from a secondary to a tertiary, as is shown right here. Now, you might be wondering, well, a tertiary carbocation, man, that can't rearrange. That's never going to rearrange because it's the most stable that you showed me on that table a few minutes ago. There are exceptions to that. A tertiary carbocation typically won't rearrange unless you end up with something that's going to be resonance stabilized. So here we have a tertiary carbocation, not stabilized by resonance whatsoever, but if we do a hydride shift, we end up with a tertiary carbocation that's resonance stabilized. That is an allylic carbocation right here, and that is even more stable than a tertiary, and so that is an exception where that would happen. Okay, I think that's enough of looking through all that, and so what I want to do now is take a look at the practice problems, and these come straight out of our textbook, in case you didn't notice. Question 6.37 asks us to do nothing more than draw curved arrows for each step in the mechanism. But what we are going to do is we're going to draw the arrows, and we're also going to label each step. Is it a nucleophilic attack, a proton transfer, a rearrangement, or a loss of leaving group? So let's start with the very first one. And again, I recommend that you either download this PDF. Again, it's in the Chapter 6 module. I recommend you either download the PDF and use it on a Surface or tablet, or that you print it out, because drawing these molecules, it takes a lot of time, okay? Back in the day when my students had hard copies of the textbook, especially if they bought used copies, they would just write the mechanisms right in there in pencil and then erase them if they wanted to. But we only have an electronic version now. So what is going on? We've got our hydroxide. It's got 3 lone pairs on it. We know that hydroxide is a strong base, but it's also a good nucleophile. And you can see that we're forming a bond right here between this oxygen and this carbon. Thus, this must be a nucleophilic attack. I start with the tail of my arrow on a pair of electrons, and it's going to have to go all the way over to this carbon. Here, let me draw it a little bit better. Like that. The tip of my arrow is going to end up on this nucleus. Now, I don't even have to do a full treatment about how electrophilic is this carbon. First of all, it's got an oxygen attached to it, so it's probably electrophilic. But second of all, I can see the product over here. So I know that that nucleophilic attack occurred. However, if I was to just leave the arrow like this, it would be wrong, because this would presume that you would have 1, 2, 3, 4, 5 bonds to carbon. Carbon cannot have 5 bonds. But if we inspect the product, we see that this bond is broken. So what we're going to do is we're going to take that pair of electrons and we're going to make a new pi bond here, which we see right here. We also see that this bond is broken. And so we're going to take this pair of electrons and we're going to make this pi bond. And then lastly, we see that this pi bond is gone. And so we're going to take the pair of electrons on that oxygen, which already has 2 lone pairs. We're going to break that bond and put the pair of electrons on the oxygen. Now the oxygen is surrounded by 1, 2, 3, 4, 5, 6 electrons, and it has a negative charge. So how would I describe this step? Could anybody tell me? Would this be a proton transfer, loss of leaving group, nucleophilic attack, rearrangement? Anybody have an idea about this one? It's a nucleophilic attack, isn't it? Right? Because this is my nucleophile. This is my electrophile. So this is a nucleophilic attack. The nucleophile is attacking the electrophile. Let's move on. The next step, you see that we're losing negative CH3SO3. Where's that coming from? The CH3SO3 minus is coming from all this over here. Right, the Lewis structure of CH3SO3 minus, which you should be able to draw, would be this. Yeah, like this, like that. So this is what we're losing. So that means that you're going to have to break this bond between the carbon and the oxygen here, right? Because we're losing that group, right? This oxygen already has 2 lone pairs, as does this one, and this one. So we're going to have to take this pair of electrons and move them over onto the oxygen to make this leaving group. So this must be a loss of leaving group. Well, what else is happening? You see the ring here looks very different. So we have no pi bond here, but we do have a pi bond here. And so what's happening is the pair of electrons here are making this pi bond. The pair of electrons from here are making this pi bond. And then since we have NO2, and we know that NO2 is when we have a double bond and a single bond to oxygen, like this, that means that we have to make a pi bond. So we're going to make this pi bond here between the nitrogen and oxygen. So that's a loss of leaving group that involves 4 curved arrows. And the last one, this one's kind of annoying because they've drawn this condensed, and you have to actually draw that whole thing out to show this last step. So I'm going to redraw this molecule here. So if we draw the whole Lewis structure in more detail, we end up with this. And now we're taking this and we're treating it with hydroxide, and we're ending up with this. Could anybody tell me what's happening in this step? Would this be a proton transfer, nucleophilic attack, etc.? This last step right here. You have the hydroxide, you've got a proton on here, but then it's gone. Absolutely. Absolutely. This is a proton transfer. So what's happening is my hydroxide, which is my base, is going to start with a pair of, anyhow, it doesn't matter. I'm making a bond here between the oxygen and the hydrogen, and then I'm going to break this bond here because we know that in order for an oxygen to have a negative charge, it has to have 1 bond and 3 lone pairs like that. So there you go. Here's our first attempt. First step was a nucleophilic attack. Second step was a loss of leaving group. And the third step was a proton transfer. So what I want you to do during our next break is I want you to try questions 6.36 and 6.39. Actually, why don't we just try 6.36? Then we're going to come back and we're going to solve this problem. Then we're going to call it a day. And when we come back on Tuesday morning, we're going to finish the rest of these problems, or at least most of them. And then we're going to cover section 6.12, after which we'll move on to chapter 7. So question 6.38.